Good morning to all of you. So today we are going to discuss the chapter ray optics. So there are two parts in the optics. First one is ray optics and second one is wave optics. So in this chapter ray optics we discuss reflection of light, refraction of light and related topics. And in wave optics we will see interference, diffraction, polarization and related topics. So regarding the light, light is an electromagnetic wave and it is transverse in nature. So light is electromagnetic wave. Light is electromagnetic wave and it is transverse in nature. And it is transverse in nature. So wave is associated with its frequency, wavelength and its velocity. So equation for that relating them is C equal to nu lambda. C's velocity of light depends upon the medium. As medium changes, there will be change in the velocity. So C equal to nu lambda, very important relation. In a given medium, velocity of light is constant. So there is a reciprocal relation between frequency and wavelength. So for a given medium means that medium, particular medium, you take it as air medium, okay, glass medium, water medium, etc. Then C will be constant. So in that case, there is an inverse relation between frequency and wavelength. If the wavelength is less, then frequency will be more and vice versa. Energy of light rays or light wave is given by Max Planck. It is given by the equation E equal to h nu. Second important point regarding this. Energy is given by energy of light. Electromagnetic wave, its energy is given by E equal to h nu. So energy is depending totally on frequency. So E equal to h nu. And don't come join with your device name. If you are coming with your own name, I will admit, otherwise I will not admit. Some are coming with Z70. I will not admit at all. Today I am giving, just inform others also. Okay. You change your name, school name, come with your proper identity. Otherwise I will not admit. Okay. So E equal to h nu. That the energy is given by E equal to h nu. Greater the frequency, greater the energy. So we are dealing with light and we can see only the visible 7 colors, that is a Vibgyor spectrum. So Vibgyor, there are 7 colors, we can see them. And violet is having least value of wavelength. And red is having, that means longest wavelength. The wavelength of violet is less and wavelength of red color is more out of these 7 colors. Exact value we will discuss in the chapter electromagnetic waves. We have to learn the exact values too. So wavelength of violet color is less and wavelength of red color is more. A very important point all should know. So which color is more energetic? Violet color or red color? The wavelength of violet color is less, the frequency of violet color is more. frequency of violet color is more and red color frequency is less. Frequency of red color is less. So energy of violet color, violet ray photon is more energetic than red color. Energy of red color is less in comparison with the violet. Okay. So which is more, according to Max Planck, you know, energy, the radiation consists of packets of energy called quanta. If it is a light ray, we call it as photon. So which is more energetic, is the violet ray photon or red ray photon? This was a board question of 1 mark and you have to explain for that. So you have to give like this, E equal to h nu. Wavelength of violet is less, therefore its frequency is more, therefore energy is also more in comparison with red color. So this is the first point. So light is an electromagnetic wave. It is transverse in nature, and how we produce them we'll see on the way. And wavelength, frequency, velocity relation is given by C equal to nu lambda. All of you are familiar with that equation. And energy is given by E equal to h nu. This was given by Max Planck. Greater the frequency, greater will be the energy. So next point is, so we are discussing with the ray optics. So light has dual nature. So first one we discuss coming under ray optics, and second one we are discussing with what? Wave optics. Particle nature, light travels along straight line, which we discuss as ray optics. Another is it behaves also just like a wave. So there are many other phenomena that can be explained only with wave theory, wave concept. So that we will see in the next class. Okay. So when light is moving from one medium to another medium, say if it is moving from air to glass or from water to glass, so one medium to one transparent medium to the other transparent medium, we see three kinds of process there, three types of process. One part of light is reflected. The second part of light passes through the second medium, that we call it as transmit, that we call it as refraction. And some other part will be absorbed by the medium, second medium. So one part of the light will be changing the path into the same medium, that we recognize as a reflection of light. And second one, some part will be passing through, transmitting through the second medium. That transmitting through the second medium phenomena we recognize as refraction, and which part to hai, that will be absorbed by the second medium. So three processes are there: reflection, change in the path of light into the same medium from a boundary. Second part, going from one medium to the second medium, transmitting, that is called refraction, then changes its path. And third one, the third part will be absorbed. We are mainly discussing with the first and second, that is reflection and refraction of light. And if the surface is extremely polished, तो majority light है और reflect करके आएंगे. Majority of the light will be reflected back into the same medium. Just like a polished surface, just like a mirror. Mirror surface, one of the side is extremely highly polished, whether it is a plain mirror or curved mirror, spherical mirror, concave mirror or convex mirror. So वहाँ पे तो majority light is reflected. So we are discussing, first point is the reflection of light from highly polished surface. So what are the laws of reflection and what is the meaning of reflection, etc. point we are discussing. So reflection of light, that is the first point. Reflection of light. So mainly we are discussing from highly polished plain mirror, spherical mirror in the form of a concave or convex. You can see three kinds of surface I am marking here on the board. First is a plain mirror. One side is polished highly, and this is your concave mirror, and this is your convex mirror. One surface is completely polished. So reflection means change in the path of light into the same medium. वापस same medium में आएंगे तो दूसरा medium में नहीं जा रहा, बिल्कुल नहीं जा रहा. Changes in the path in the same medium by obeying some laws. So what are the laws of reflection? We'll see from the diagram. So to the mirror surface, you take a point P which we recognize as the center or the mirror, we call it as a pole. Drew a normal to this perpendicular to the point P. These are normal. So these are the normal that is drawn to the point P. P can be taken as the center point of the mirror, can we call it as a pole. The normal I have made there. Suppose a ray of light is reaching to the point P at an angle. Usually we call it oblique incidence. Okay, it's a plane mirror. This is the ray incident. It is called incident ray. वो आगे नहीं जा सकता. It cannot go further. अगर जा सकते तो dotted line बना रहे में इधर नहीं जा सकते. But it reflects back into the same medium. Changes its path through this much angle में, that changes in path and going to the same medium. That is called reflection. Reflection के अंदर the light is coming to the same medium, so कोई change नहीं है velocity में, कोई change नहीं है frequency and no change in the wavelength. So three parameters C equal to nu lambda, all are remaining constant. So C equal to nu lambda, all will be constant. C will be a constant, there is no change. Frequency constant, no change, and wavelength also no change, remains constant. So this is only the phenomena where all three things are constant because light is coming back to the same medium from a highly polished surface. And when it is doing so, this angle of incident ray, this is a reflected ray, angle between incident ray and normal, we call it as angle of incidence. And between the reflected ray and normal, we call it as R. And here I is equal to R, it is obeyed. Angle of incidence is equal to angle of reflection. So through what angle it is deviating from the initial direction? So I extended the initial direction of the incident ray here. So this is the initial direction of incident ray. Either nahi ja sakte. So from here the ray is deviating through this much angle. So the deviation produced in this case is equal to total angle is 180. I and R are equal. And so we can write 180 minus 2I is the deviation produced by this ray. Reflect ray undergoes a deviation. Itna deviate karke coming back to the same medium. And these incident ray, normal, these three things are there. Incident ray, normal and reflected ray all lie in the same plane. So these are the two laws of reflection. Angle of incidence equal angle of reflection, and incident ray, normal and reflected ray all lie in the same plane. It is applicable for all kinds of surfaces, whether it is a plane, curved in the type of concave or convex. You can see in figure 2 and 3. So here this is oblique incidence, incident ray, angle of incidence is I, reflected back, this is R. Deviation is also same value of deviation, D equal 180 minus 2I, that is the deviation, it is same for all. And here this is a convex mirror, incident ray IR, angle of incidence, and it is reflected. This is R, and it may be a deviation, that is D equal to 180 minus 2I, the deviation produced by reflected ray. Steffi, can you hear me? Can you tell me what, how is the volume? Can you unmute yourself? Is there any option there? Okay, we are continuing with the next point. So these three diagrams, all of you observe it. Next, a special case, suppose a ray of light is going to a mirror surface along its normal itself. What is the angle of incidence? And what will happen to that ray of incidence? Light is traveling along a normal and strike the mirror surface, then what will happen to it? So this is the case here. I am marking as a plane mirror to the point P. This is the normal, and the light ray is going along the normal. What is the angle of incidence? This is the normal to the point P. Angle of incidence in this case is equal to 0. But I is equal to R, therefore R is also equal to 0. The light ray retraces its path, rebounds, comes back. So this is called normal incidence. When a light ray reaches to a polysurface, mirror surface, along the normal, the light ray retraces its path. I is equal to 0, R is equal to 0. This is, we call it as normal incidence. So during reflection, there is no change in the velocity, no change in the wavelength, no change in the frequency. Board question. Velocity of light in air or vacuum is 3 × 10⁸ meter per second. You have to remember the value. 3 × 10⁸ meter per second is the velocity of light in air or vacuum. Okay, I am giving an example that is for during the reflection. Suppose incident wave has a wavelength 4000 angstrom. 1 angstrom is 10⁻⁻10 meter. Okay, light traveling in air strikes a mirror surface with the wavelength is given as 4000 angstrom, and angle of incidence is given to you as 30 degree. Angle of incidence is 30 degree. You have to find out what is the deviation, what is the frequency of reflected light. What is the frequency of reflected light? So what is the deviation produced? The angle of incidence is given to you. The diagram is already there. Any kind of diagram you can take, plane mirror or concave mirror, convex mirror, any diagram can be selected. Angle of incidence is 30 degree. So deviation is, equation is already given there, 180 minus 2i. So deviation you can write. Angle of reflection is also same, 30 degree. Yeah? So deviation, angle of reflection is 30 degree. So deviation is 180 minus 2i. So that is 180 minus 60. So 120 degree mein deviation hai. And next point is, what is the frequency of the reflected light? Incident light wavelength is given to you. Incident light wavelength is given to you, but you are asked to find the frequency of reflected light. So the first point you have to recognize is that there is no change in the wavelength, whether for reflected light or incident light. Wavelength remains same. So reflected light can be wavelength same. There is no change. So frequency of incident frequency and reflected frequency remain same. Calculate the value. So C equal to nu lambda equation we can use. So frequency is equal to C by lambda. C, you should remember 3 × 10⁸ meter per second divided by wavelength is in angstrom. You have to convert into meter. That is 4000 angstrom. 4000 into 10⁻⁻10 meter. Okay, this is 3 × 10⁸ divided by 4 into 10⁻⁻. 3 zeros cancel and you are getting 4 × 10⁻⁻7 meter per second and meter cancel hoga. And this is 3/4 into 10⁻15 per second. We call it as it is a hertz. Unit of frequency, the hertz, 1/second, second to the -1, we recognize it as hertz. So 3/4 is 0.75. So frequency is 0.75 into 10⁻15 hertz. But there is scientific way of writing the measurement. You put the decimal point after the first digit. So frequency, we'll write it as 7.5 into 10⁻14 hertz. It was a simple board question. You can remember this. Okay, next point. So we are defined what is the principal focus of a concave mirror and convex mirror. Principal focus. Next important point. So we are mainly discussing with spherical mirrors, concave or convex. Define principal focus of a mirror, especially spherical mirror. This is your concave mirror. This is your convex mirror. The center of the mirror, we call it as P. That is called pole of the mirror. P stands for pole. And these are the part of the sphere. Therefore, there will be a center too. Concave mirror, the center is towards left side. That we call it as center of curvature, C. And for convex mirror, and you can see the center of curvature on right side. A straight line passing through these 2 points, center of curvature and pole, is called principal axis. So what is the principal axis of a mirror? Principal axis of a mirror is a straight line passing through the pole and center of curvature. So P is the center of the mirror, we recognize as a pole, and C the center of the curved portion, that depending upon the curve you can recognize the C. Where is C? Concave mirror, it is on the left, and convex mirror, it is on right side. Next is, suppose you consider an object very far. Example, light rays coming from the sun. So far off place object, infinite object. So object at infinite distance, the rays are parallel. So this point will recognize later on the way, in way optics we will see why the rays are parallel. So if the object is at infinity, rays are parallel, and they can be parallel to principal axis also. After reflection, object at infinity, after reflection, they converge to a point, coming to a point on the principal axis. This point we call it as principal focus. Next case, in the case of convex mirror, rays are again parallel, object is at infinity. So this ray, in front of the rays, you can put 2 dotted lines to show that they are coming from far off places, object at infinity. After reflection, what will happen here? After reflection, it appears to come. So from a point. So after reflection, it goes in this way. So rays are coming like this, appear to diverge, appear to come from a point F on the principal axis. If somebody is here on left side, for them, the rays appear to come from a point F. I say like that. So these rays after reflection appear to come from a point F on the principal axis. And this point is called principal focus of a mirror. So definition of principal focus, combining with 1 and 2. Rays parallel to principal axis, considering the object at infinity. After reflection, in the case of concave mirror, converges to a point on the principal axis, or in the case of a convex mirror, appear to diverge from a point on the principal axis. This point is known as principal focus. And the distance between the pole and the principal focus, we call it as focal length. Focal length represented by small f of a mirror. What is the focal length? It is the distance between pole and focus. That is represented by small f, focal length. So it is the distance between pole and principal focus of a mirror. We call it as focal length. On the way, we will recognize, we usually consider the rays very close to the principal axis. So there are 2 kinds of rays if you are considering with huge kind of mirrors. So this is your principal axis, P, C line. Rays very close to principal axis, or rays those who are far away. 2 rays I am marking here, 1 and 2. The second ray is very far from the principal axis, both dur. So we call such kind of rays are called marginal rays. Marginal rays, far from. We put a margin on extreme left on right side of your page. Marginal rays, thoda sa dur line banaye. So this ray we call it as marginal rays, and rays comparatively closer to the principal axis we call it as paraxial rays. Paraxial rays. Usually, if the object is at infinity, the rays, these two rays may not come to same point. So, thoda sa different points may they will come and meet, so the image formed will not be bright. So, marginal rays and paraxial rays, in the case of a huge mirror, they after reflection will not come to the same point. They may slightly different points, they will come and meet. So the image formed will not be clear. So there will be a problem in the image. So what we say, so image is not brighter in such cases. So this problem in the mirror is called spherical aberration. So this we call it as spherical aberration. On the way, we'll rectify and we'll use such kind of mirrors in telescope. That time I'll explain. But I'm using the word here, spherical aberration, A-B-B-E-R-R-A-T-I-O-N, spherical aberration. Means rays, paraxial rays and marginal rays after reflection will not come and connect to the same point, come to the same point. So focus may, so there will be slight change in the position. So the image form will not be bright or clear. And such defect we call it as spherical aberration, can be removed. It can be removed by using some technique. On the way I will inform you. So next point is next is what is the relation between focal length and radius of curvature of a mirror. So what is the radius of curvature and what is the focal length? Radius of curvature is, suppose you are given a mirror here, concave mirror. This is P, this is C. C is the center of curvature. The distance between P to C, that we call it as radius of curvature, R. And this is the focus. Distance between P and F, we call it as focal length, small f. In the case of mirror, the relation between them is F equal to R by 2. Focal length of a mirror is related to its radius of curvature by the equation F equal to R by 2. And it is constant in all medium, whether it is air medium, even if you keep your mirror in water, there is no change in the focal length, F equal to R by 2, no change. So, focal length is independent of the medium in the case of a mirror, but for a lens, we discussed there, for a lens, it depends upon the medium. So, focal length of a mirror is 30 centimeter in air. Focal length of a mirror is 30 centimeter in air, and what will be its focal length in water? The focal length in water will be same as focal length in air, there is no change. So focal length in water is equal to focal length in air, that is equal to 30 centimeter, there is no change. And this is equal to half of the radius of curvature. Next important point, how you derive this equation? Derivation is required. How to derive the equation? Relation between F and R. So before going to this derivation, I will explain different kinds of rays that we consider for image formation. So we have plane mirror, we have concave mirror, we have convex mirror. We have to get the image. So plane mirror produces always virtual image. Concave mirror produces virtual and real image. Convex mirror always produces virtual image. So we have to see image formation and its location. For that, we have to consider some different rays are to be considered. Okay. So some rays are to be considered. So that is the next point. So all of you can recognize what are the different rays to be considered for image formation. Minimum we require 2 rays for its image formation. After completing this, we will go for the derivation of F and R and other procedures. First, in the case of concave mirror, And convex mirror, I am explaining the thing together. Concave mirror, ray parallel to principal axis. Ray parallel to principal axis. After reflection, passes through the focus. A first ray we consider in all cases. All cases this ray will be considered. In the case of convex mirror, ray parallel to principal axis. After reflection, it appears to come from the focus. This is ray number 1. So ray parallel to principal axis. After reflection passes through the focus in the case of concave mirror, and ray parallel to principal axis in the case of convex mirror after reflection appear to come from the focus. This is the first ray, and this ray we have to use in all cases. Second one, just reverse of this. If a ray of light is passing through the focus and reaching the mirror, a ray of light is passing through the focus and reaching the mirror, after reflection becomes parallel. A ray of light passing through the focus, after reflection becomes parallel, just reverse. In the same way, the diagram can be used for convex. This is the focus. This speciality is here. Suppose the ray is coming from here and that tend to go to principal focus. It cannot go there. If we extend, that may touch the principal focus. In such cases, after reflection, the ray will be reflected back, reflected in this way, parallel to principal axis. Reflected parallel to principal axis. This is the case 2. Case number 3. Convex mirror. This is the pole and this is center of curvature. If a light ray is passing through the center of curvature, light ray is passing through the center of curvature, any line passing through the center, that is the center of a sphere. It's a radius or diameter that is always normal to the surface. So when a light ray is passing through the center of curvature and reaches to the mirror surface here, concave surface, angle of incidence is 0 here. So angle of reflection is also equal to 0. It reflects back. It is a normal incidence. This example is a normal incidence. It is a normal incidence. It's a normal incidence. Okay, it's a normal incidence. So ray passing through the center of curvature, after reflection in the concave mirror, it reflects back. It is an example of normal incidence. Same diagram you can go for convex mirror. Convex mirror, the diagram is here. This is the P, this is center. So same way, if you draw a ray of light, that is, if you are extending, that may touch the center of curvature here. So rays tend to reach the point C. Why nahi ja sakta hai? Tend to reach the point C. After reflection, but it's a normal incident at this point. It's a normal incident. I is equal to 0, R equal to 0. Therefore, the ray will be retraced, reflected back. It's a normal incidence. It's a normal incidence. One more ray we consider. That is fourth ray. So that is also important one. We usually make first one. We'll take. Ye to very important. Ye to always we consider. And third one also we'll consider. And next ray is case number 4. If a ray of light that is reaching here at an oblique incidence, I call it as an oblique incidence, then what will happen to you? So the light ray, this is the number 4th case, the ray reaches here at the pole obliquely. It's called oblique incidence by making an angle at the point P and reflects back by obeying the laws of reflection, that is I is equal to R.